okay? Okay. Hi, everyone. So as Andrew said, I'm Sarah Loebman. I'm a Hubble Fellow and also a UC Davis Chancellor's Fellow. That means if you're a part of the UC system, you should hire me. I'm an easy get. If you want to know more about that, talk to me afterwards. I'm really grateful for the opportunity to talk about the work that I've been doing with Andrew Wetzel and the rest of the FIRE team. And of course, I'm really lucky that he introduced the simulations thus far. So I'm just going to dive straight in to be talking in particular about the disks today, and to hopefully give you a good sense of why I feel really good about these disks for deriving understanding about L-star-like galaxies. So first I'm going to start with a wonderful movie that Shay made of one of our Latte sims. This one, there are a couple things I want you guys to take away. One, this is just the stars. And I want you to really see that at early epochs, these have a vigorous, enthusiastic kinematic history. But by roughly redshift 0.7, 0.8, things start to settle down, and I'll give it a moment to get there. And really what I want you guys to see is that as things settle down, we start to see the rise and fall of transient spiral structure. You see a bar form, and all within the larger cosmological context, right? So there's all sorts of incredibly interesting dynamic processes that are going on that are influencing the stars that we think stars in the Milky Way likely experienced, and we see them all together in this particular system. So I'm going to talk about three things that I think we should be asking all our simulations if they're able to replicate. I think they're really, by and large, most simulation groups get this right, and I think that it's an important test to see, first order, do we believe these disks are good Milky Way-like galaxies? And so the first thing that is near and dear to my heart is thinking about the structural distribution of stars. And in particular, what I am used to thinking about is the structural thin and thick disk. So on the left here, I'm showing you a plot from Peter Yoakum in 2006, looking at a bunch of external disk systems and looking at as you look up and out of the plane of these disks, you see that as you go to larger and larger heights, that you're seeing older populations. And the density of stars in these galaxies are really well described, not by a single exponential, but by a double exponential profile. The same, of course, is true of the Milky Way. Since the days of Gilmore and Reed, we have known that there is not a simple exponential profile as a function of height out of our midplane, but instead that the stars are better described, as shown by Mario Urich from the Sloan Digital Sky Survey data, that by a double exponential profile. So the first thing I think is really natural for us to ask of any disk-like system is, do we replicate that double exponential profile? And as Xingxing Ma showed in 2017, the Latte sims do a really nice job of this. So if you look at roughly the solar cylinder, and you look at the density of stars, that's what these points are showing here. If you go up out of the plane of the disk, try to fit it with a single exponential profile, which is what is shown by this dotted line here, it doesn't do a good job fitting the data. Instead, you need to move to a two-component fit. What is particularly nice, if I can advance, apparently I can't advance, but if my second plot showed up right here, right now, you would see that the most of the stars up and out of the plane of the disk in the Latte sims happen to be older population. That is both for the Milky Way and for the larger population of external galaxies, disk galaxies, and for the Latte sims. Two-component fit with an extended older population does a really good job of describing the structural distribution of stars. Moving on to think about kinematics, and just something that we probably had beaten into us early on in the simulation days is just globally, what do we expect for a disk-like galaxy to look like for circular velocity as a function of radius? And so on the top left here, I'm showing recent data that was published from Glenn Hawthorne and Ortland Gerhard's 2016 review of Milky Way data. And what they present here is a whole bunch of really, really well-measured, precise circular velocities for stars in the Milky Way. And as you can see, This black line here shows the rotation curve for the Milky Way. It nicely flattens out as you get to larger radii. This, of course, is true when you look at, as Vera Rubin taught us, at all disk systems nearby, and all disk systems in general. And you can see as you get out to 10 kpc that the systems flatten out nicely. Now, at small radii, you see a range of inner morphology. But once you get beyond, say, 5 kpc, all these disks flatten out nicely. It's kind of average or global kinematic properties. The same is true, of course, of Latte as well. When we get out to beyond 5 kpc, we have this nice flat curve, regardless of which of the 8 systems we look at. So hopefully thus far I've already convinced you the structure of these disks look good. The overall global kinematic profile looks pretty nice. The other thing we should ask ourselves is, what does the chemistry look like? And just very briefly, we can either fix ourselves at a particular radius and look at up and out of the plane of the disk, the trends in metallicity, or we can fix ourselves at a particular height in the disk and look at the trends as a function of radius for metallicity. And regardless if we do that, either one of these things, we see that the trends in the simulation, where showed in the dashed lines here, match the observational data very well. So that is, at fixed radius or at fixed z, you see roughly a negative or flat metallicity gradient, depending where you look. And we're matching the overall observations of the Milky Way particularly well. So hopefully at this point I've kind of convinced you that the global average properties look pretty nice. I'm now moving on to talk about kind of taking a step beyond and thinking not just about average properties, but now looking to think about scatter and velocity dispersion and what we can gain from the simulations beyond averages. And in particular, I'm going to pause for a moment and kind of harp on this age-velocity relationship. I'm not the first person to talk about this. Many people have thought about this before, but there's a particularly salient time to start discussing this because, of course, Gaia is giving us lots and lots of stars with very well measured velocities. And in the era of, say, surveys like Kepler with asteroseismological overlap, with things like apogee, we're getting much better measurements on things like age. Okay, so quickly, just to remind you, if you don't often think about velocity dispersion, I can pick you up, I can put you out in the Milky Way's disk. I can say, gather up a whole collection of stars and make a histogram of the velocity of those stars. You can take any component of velocity you want. In this example, I've just shown you the component of velocity in the r direction. I've made a histogram here. And of course, because the Milky Way's disk is neither expanding nor contracting, the average quantity is at 0. The next most interesting quantity to measure is the scatter or the dispersion, the standard deviation, all the same thing here. This is represented by sigma r. And in this particular case, it's 75 kilometers a second. Okay, so for the Milky Way, what people have done for a long time now, and particularly very well done for the Geneva-Copenhagen survey, was they went and they took stars and bin them as a function of age and tried to measure the velocity dispersion to see what happened as a trend in age. And that is what is shown here. So regardless if you look at sigma r, sigma phi, or sigma z, you see as you go to older and older ages, the velocity dispersion goes up, right? In a nice, smooth, very well understood, well, nice, smooth trend. Okay? This is for the Milky Way. Now, one of the things that's really interesting to me is to think, is this unique to the Milky Way? Do all systems look like this? And what is particularly nice, of course my plot is cut off right now, but what is particularly nice is that a couple years ago, Claire Dorman, who came out of UC Santa Cruz here, went and looked at the same thing, but instead for the Andromeda galaxy. And what she found was that if you look as a function of age on this axis, instead the Milky Way data is down here, but if you look at the M31 data, Andromeda data, it has a much steeper line here. That is, M31 has a considerably higher velocity distribution. It's much hotter age-velocity relation. Okay, so I had given you an argument that Latte is particularly wonderful in a lot of different ways. Right? One of the things that I think is really interesting for us to think about is how are we doing for things like the age-velocity relation. Now, I have showed you 8 different Latte simulations right here and the age-velocity relation. I've also overplotted Claire Dorman's results and the Milky Way's results. As you can see here, Latte is strongly consistent with the M31 results, less consistent with the Milky Way. A result like this has also been shown in other simulations, particularly the Riga simulations find something very similar to this. The question becomes, is the Milky Way an outlier? Or is there something that we have yet to model better in the simulations? And this is something that we're ongoing investigating. We're looking at the effects of how cosmic rays can affect the velocity dispersions and better modeling of the radiative hydrodynamics to see how it affects this in the near future. So this is ongoing work and something that I think that we should be asking ourselves how we're doing in all of our simulations. And very quickly, I want to point out that other people have looked at this in the past, particularly John Bird looked at this in the ERAS simulations, and he came up with this idea that disks grow inside out, upside down. And he found from analyzing that simulation that stars are born hot, and they don't change much from the time they're born. In a complete 180-degree turn from that, Marie Marteg found in 2014 from simulations that the stars are born cool and then heat with time. So there's a big tension here about what's actually physically happening. And I want to say that Latte we actually find it's a combination of the two things here. So on this axis is age at stars at present day. And I want to say at redshift 2, we can look at what the velocity dispersion of these stars were. Already pretty high, already at 40 kilometers a second. Now if we march down to redshift 1, these stars have bounced up to 80 kilometers a second. If we then go to redshift 1/2, we've bounced up further and in a very self-similar way. And finally, at redshift 0, you can see that all these populations are hot. So born hot and continue to heat over time. All right. The other really interesting thing when we're thinking about not just average trends, but scatter, is we can start to think really critically about the chemical history of our galaxies and how, if we're matching our best observational results. Now, we have detailed observations of the Milky Way, and some of the detailed observations of the Milky Way coming from surveys like Apogee are somewhat confusing. So before I talked about the structural thick and thin disk, we also have a chemical thick and thin disk, or chemical bimodality that's been found in Apogee, as David Nadiver showed here in his 2014 paper. So on this axis is iron, on this axis is alpha abundance, and what you see is there are two different tracks in data. So what's going on here? In the Milky Way, if you look at different radii as you go further and further out, the strength of these different tracks change. The question becomes, is this bimodality universal to all galaxies, or is it just unique to Milky Way or a subset of galaxies? What is this telling us about the dominant chemical processes that are shaping our galaxies? Well, as of yet, we only have the Milky Way to measure this bimodality in. But we can look at some of our simulations like Latte and think very deeply about what we're seeing in a large sample of simulations. Okay? And so I should note that lots of groups have tried to get chemical bimodality right in the past. Auriga has hints of getting it right, finding multiple tracks, up to 3 tracks. However, I would make the argument that Latte is hands down the most elegant and best matching to the Milky Way that I've seen. On the left, you can see the distribution of stars for the high alpha stars, and on the top and the bottom, you can see for the low alpha stars. Very different physical distribution. On the right, you can see 2 clear different tracks for a global, for the disk for an overall one of our SINs, M-Q. We have 8 galaxies. 2 of them show this bimodality. That says that roughly 25% of our galaxies, of L-star galaxies, are showing this bimodality. And how is this generated? This is generated from gas-rich early mergers, all of the mechanism that Chris Brook talked about in 2016. I have more that I wish I had got time to get to. If you're interested in talking about the azimuthal dependence in metallicity and what some really interesting trends that we're seeing and that are comparable to observation of gas in external systems, which is relevant for things like MANGA and other external surveys, or if if you're interested in the star cluster formation and how star cluster formation is dispersed and the scatter, the range in FeOH we see as a function of angle, and how that is relevant to chemical tagging, and whether or not we can actually use chemical tagging to backtrack star clusters, like is proposed in Galah, I would love to talk to you about it afterwards. Thank you, guys. So I actually haven't been looking at that. Andrew, do you have an answer for that?
Well, I can say is we did a paper out a few weeks ago, Victor David Tuesday was looking at a case study. One of our systems happens upon a pretty significant pseudo-harshness scale, far that functions into a sort of a pseudo-ball play. So that clearly happens, although I wouldn't say it's common. I think that was the one system we've seen where that was a pretty clear cut.
So at the risk of sounding anti-Loebman, would you agree that what Fire is seeing here as far as mass assembly and star formation history is really Serlin's in?
As opposed to ELS? Yes, I would.
As opposed to ELS?
Yeah.
Right. So just to remind everybody, Serlinson said, no, there were a bunch of little galaxies, and a lot of them got broken up and dispersed in the process of making the bigger potential black.
As opposed to monolithic collapse.
Yeah, exactly.
Yeah, I think that's a fair assessment for what we're seeing.
You should reference that.
For sure. I will, I promise.